Hello, good morning, good afternoon, welcome. This is the second in our series on CAN FD, brought to us by our good friends at Embedded Systems Academy. Today we have Olaf, who's going to be talking about stack porting and secure bootloaders. They'll be mostly talking from Olaf with a couple of little updates on some products from me on the LPC product line. So without further ado, over to Olaf.
Thank you very much for the introduction. So my name is Olaf Pfeiffer from the Embedded Systems Academy, and I'm doing the second part. For those of you who did not have a chance to see the first part, I'll do a brief review that's just 2 slides or so. So in case you missed it, just to make sure you have the basics. So for this webinar content, we'll do the review, as I just said, a few slides. Then we'll look at the implications on higher layer protocols. When you start using CAN or CAN FD, typically you use some other software and stacks around it. So we'll review how to use these stacks, what are the implications here. And then we'll look at bootloaders. What are the implications for bootloaders, including some of the security risks, and could ransomware be a potential security risk? This is nothing we put in here today. It's pure coincidence that there came up so many issues this week again. The slides are older, but we wrote a blog recently just already warning a little bit of could ransomware potentially go embedded. And of course, when we talk about bootloaders, that's how code gets in there, and we have to see if we can make it secure enough that nobody can introduce malicious code. And so the bigger part of this presentation will be about secure bootloaders, talking about protection levels, some of the basics and key management and so on. Us, the Embedded Systems Academy, was founded in 1999, and we initially started with purely consulting and training, but over time our main focus today is more on firmware and software. So we are a provider of software for various CAN open stacks and bootloaders, and we also provide a variety of software. Also, we have been doing the NXP's Flash Magic software for, must be 15 years or so now. Brendan, do you recall? Well, no, it's quite a while. And we participate also in CAN open standardization issues. So the CIA, the CAN in Automation Users Group, is responsible for a lot of the standardizations, and we are an active participant in those groups. Let's do a quick review. CAN FD, the controller area network, is around for 25 years or so or more, and it's good. So why would we need to change something, specifically if it involves new hardware? Well, the data rate is not really rocket science. CAN was always limited to 1 megabit. And so Bosch came up, the inventor of CAN, with something called FD, the flexible data rate. And as you can already see a little bit here in the screen, it's all about having another data rate, another clock rate during the data phase. So for a quick review, what are the main differences between CAN and the new CAN FD? It's that we now have mixed bit rates. So besides the regular rate, which is now named the nominal rate, which is still used for the control fields, we also have a data rate. And the data rate can be a multiple of the nominal rate, and this is used for the data field and the CSC. Now, why couldn't we speed up the entire message? Well, that is because the arbitration mechanism in CAN really requires that 1 bit is stable on the entire bus before you can start transmitting the next. And so they really couldn't touch that to keep CAN working as it is. However, this method of a bit that can be overwritten in 1 bit time is not used during the data field, and so that's why we can speed up there. Well, what are the changes? Besides the bit rates, we now have more data per frame. A message frame was always limited to 8 in the past. Now we can do up to 64 bytes. Nice thing about the bus topology is that the wiring can stay the same, so you can still use the same old wiring. However, we have to say that it becomes more sensitive on higher bit rates. So in the past, if you used the system, let's say at 125 or 250 kilobit, Well, it would even work if one of the termination resistors was missing or an extra one was inserted and you had extra tab lines or maybe even a star topology. Well, with CANFD, you really have to go back to the basics, to the book, and say, well, if you do your physical network layout, it really needs to be one network strand with two termination resistors at the end and no tabs in between. Now, the last point here, the node CANFD is enabled. Of course, CANFD is somewhat backwards compatible in being CAN-like. However, the old classical CAN controllers that are out there, if they see a CANFD frame somewhere on the network, on the bus, they will destroy it because they don't know it. There are changes in there that will make them destroy the message. So if you start to use CANFD, you have to make sure that all active CAN nodes connected also support CANFD. And there is a little exception. There are some CANFD ignoring transceivers. So if you use a classical CAN device with such a transceiver, then although it cannot participate actively in CANFD communication, it would not destroy those. And there's only one more slide to go for me on CANFD basics here. Let's just review the message and the message frames. So we have start of bit, then comes the arbitration field with the CAN ID and the control field. And the biggest change is that in the past, when you looked at CAN frames here, it would still say 0 to 64, but then down here it would say bit and not byte. So now we are up to 64 bytes, and the CSC had to get a little bigger to be good enough for the extra data in here. Again, where do we speed up? So the speed up phase excuse me, begins somewhere here in the control field. That's where we speed up, and all the way through the CSC until the end of the CSC we have the higher data rate, and then go back to the nominal bit rate. Let's just review one more feature, the DLC, the data length code. In CAN, that has always been 4-bit. However, in classical CAN, you would only be allowed to use values from 0 to 8 because the CAN messages were limited in classical CAN up to 8 data bytes. Now, in CANFD, we can use the full value here from 0 to 15, and here is the extra values and how they were assigned to data sizes. So in order to be able to do 64 bytes, they didn't extend the data length code. It's still 4 bits. They simply are interpreting it differently. So if you say data length code is 10, for example, then the real length is 16 bytes. If you say 13 as data length code, the length is 32 bytes. And so the biggest message we can have is with a data length code of 15 is of 64 bytes. And with that, I would like to end the recap of what CANFD is and jump to the higher layer protocols. When you start using CAN or CANFD, you typically have some software on top of it referred to as a communication stack with layers, layered communication, and I'll just use CANopen and J1939 as some of the examples, what's out there, what is used. And whatever you use, remember it's somewhat a hard transition because we just already said we cannot really mix classical CAN and CANFD. As soon as we start communicating in CANFD mode, we have to have all nodes communicate in CANFD mode. For everyone doing software stacks, the benefit now is you don't really have to think too much about backwards compatibility, because once you have CANFD running, well, everyone will be new nodes, and so you might take advantage of it and do things that are a little bit disruptive to what would have been on a regular upgrade path. But as you don't need to worry about this and we don't intermix, so almost start over, you can be more creative here. So the the first step that everyone typically does is, of course, you start repacking your messages. In the past, we would only allow 8 bytes, so we really want to take advantage of the 64 bytes, and everyone first checks how can we get more data or redefine our protocols to make use of that. It's still work in progress. I'll just give you an update here on CANopenFD. What's the state here? It is still under development, but the first demonstrators have been shown at the International CAN conference this year, and also at the Embedded World in Nuremberg. We already had at the CIA booth, the Canon Automation booth, a demo running also involving this LPC 546 family plus some other devices, and total of 5 or so companies involved. And the number one thing that was changed is the PDOs. If you don't know too much about CANopen, PDO is a process data object, and it's really CAN IDs with process data. Those were now enhanced to support 64 bytes, of course, so that you can simply pack more data into a message. But what is the more interesting extension is now the USDO. In the past, in CAN, we would have something called the service data object, the SDO, and that would be used as a request response communication from one master to all of the slaves out there. And so what happens is that only one master or manager could use this, and the devices out there, the CANopen devices, they would send a response to the request from that manager. And so only one device was able to do this sort of communication. Well, what we did with the universal SDO is that it's now a fully meshed communication, and suddenly every device can communicate in this method with every other device. And so besides just sending the CAN IDs, you can now do things like that a device checks by itself, who else is here? Let me just read who is node number 5, and do much more analysis by themselves. The nice thing here is that it's also for any size, of course, not only limited to 64 bytes, there's segmentation included, so you can do even longer data transfers. And also something new we introduced in this mode is a broadcast mode. So these requests, when you're doing a write, they can actually be a broadcast to everyone. So you could, for instance, in one message inform everyone out there who you are and send your identification as a broadcast. Or at the high end, what we have done in a demonstrator is a firmware broadcast. We'll come back to bootloaders later, but literally we implemented that one host is sending new firmware to multiple devices in parallel at the same time as a broadcast. Looking at other stacks, we also have J1939 by the Society of Automotive Engineers. That's the Truck, Bus, Control and Communications Network Committee. Well, they are not so active. The CIA was faster. They came up with their corresponding CIA 602, which is a specification for remapping some of the J1939 application profile. And what they did is that the so-called PDOs, also the process data units that you have in J1939, they, as a first step, said, oh, to simplify use, let's simply take multiple of those in one messages. As we now have up to 64 bytes, we can take these older, smaller packages and just put multiple in one message. But at the same time, we definitely also increase potentially data sizes and allow more room for security and safety information. In the past, you couldn't do an 8-byte trailer if you only had an 8-byte message. So definitely more security and is also an issue here. Now, when it comes to upgrading your code, and you have CAN code and need to now use an FD version of it, then if you use a communication stack by a third party, then of course that company or party providing the stack should be able to provide you with a CAN FD version. You should not really need to do these changes yourself. Unless you are using your own protocol, then of course you have to do that. If this is properly done and there's a good abstraction layer in between, then there will really be minimal changes to the application interface. Allow me to summarize how we do it in our own micro-can-open source code. Our application programming interface typically uses directly so-called object dictionary accesses. In CAN-open, all parameters, everything you communicated, is packed in a so-called object dictionary. It's kind of a lookup table, and you never really directly issue or communicate with a single message. So really the abstraction layer is such that on the application interface you don't really see a single CAN message. All you do is you read or write parameters in this object of the CAN-open implementation, and if the stack is exchanged, then on the bottom it will exchange CAN-open FD messages if it's an FD stack, or it will send classical messages if it's in classical stack. Of course, the only exception here is if you start using completely new features like the mass broadcast or so. That requires some custom code, but you didn't have that in your old code, so just porting an existing code to FD when a commercial stack is used should really be straightforward. Let's look at some of the implications for bootloaders. When we change from CAN to CAN-FD, well, yeah, you can already see somewhere speed is involved here. It's the code size and update time. And if you look a little bit at the history of CAN-FD, then you'll find out that the code update, bootloading, was one of the driving factors behind the development, because the tendency was and is that code gets bigger, and if you have to run an update on classical CAN, then just even a 128K update could take a minute or more. Now imagine you have to do this on multiple devices, because maybe you have a machinery where 5, 6, 7, 10 or more CAN nodes are used, and by updating the software in one of them, you might be required to also update the software in all communication partners. And suddenly, on bigger systems, you spend half an hour or maybe even hours to update everything. And what is the reason why it's so slow? Because theoretically, even classical CAN can do 1 megabit, right? Well, the main issue here is also the segmentation, not only the speed. Because for a reliable transfer of bootloader code, you typically do this just really segment by segment. So you send a request, wait for the response, send a request, wait for the response, and so on. So over the thumb estimate is that for one such segment, you need at least 3 to 5 milliseconds, even slower if some other machinery is involved. So with that calculation, it really comes down to these slow speeds. And here CAN-FD now really kicks in, because in these individual segments, we still have to sacrifice 1 byte for flow control. So there's a segment counter in there, or how many is this the last segment, things like that. So meaning in classical CAN, for 1 segment, you were able to transmit 7 bytes. Now in CAN-FD, it will be up to 63 bytes. And even conservative estimates just say, well, your updates might be some 8 times faster. The first demo that we just tried, and this is not yet high-end optimized, can easily do the 128K in about 5 seconds. So that's quite an improvement. Again, with compatibility issues, there's one thing I would like to mention. I said earlier that, of course, you can't mix classical CAN and CAN-FD communication actively at the same time, because we would get error frames. But we have the chance to do a CAN-FD update on a new node if all the other ones are powered down. So here it really depends, or they are disconnected. It depends a little bit on your application. If you say they have 1 device, then you now introduce CAN-FD 1 at a time, that new device could operate in classical mode during regular operation. But you say, oh, during update, we disconnect the cable from the network and we plug it into a host system anyway. Well, at that point, we could enable CANFD and run at least faster updates this way. So this might be an alternative for some of you if you have a more slow migration path and cannot upgrade all nodes at the same time. We also should review bootloader risks. In the past, can open bootloaders would typically only have minimal security protections. Often the protections would be so minimal that even record and replay attack could have success. So if you were able to record the traffic communicated, to activate a bootloader, to erase the flash, and to transmit the code, you just recorded that message and stupidly replayed the host messages, yeah, that would work, and you could update other devices this way, because the idea in CAN and CAN open systems for a long time was that these are private locked systems where attackers do not have immediate access, that networks are deeply embedded in some machinery. However, what happens today is that more and more CAN open networks suddenly get some remote access. There are so many CAN devices with Bluetooth, CAN to Bluetooth, CAN to hotspot, wireless, Wi-Fi, and these things. So even a network that was never intended to have remote access might suddenly end up that some service technician or somebody who buys some sniffer dongle says, oh, let's plug this in and see what happens. And suddenly you have access with the smartphone to your CAN network. And so really the risks we have to now review. So what could possibly all go wrong? Well, if you think about that the code, your code that you're updating falls in the wrong hands, what could go wrong? Well, if it's completely unprotected, it could be easily copied to other devices. So if one of your competitors or someone else comes up with a cheaper hardware but is missing the software and they have access to your hex file, well, maybe they can just program it and copy it. So that's something we want to help you to protect. If it's not going that far, could still intellectual property be extracted? So maybe it cannot directly programmed into another device. However, maybe it can be disassembled and re-engineered and some of the code extracted and elsewhere. And latest, if we talk about ransomware, I think we really have to keep in mind what could an attacker do if they were able to modify it. And just to bring up by now still theoretical, but nevertheless the worst case scenario, if an attacker would be able to introduce his own code for while you update an embedded device, and this own code replaces the existing bootloader and throws that away, and now the attacker installs his own bootloader, you're literally locked out of your system if there's no other backup method of getting it programmed. So these are all the things that with today's adding a secure bootloader we want to protect you from. Now let's review how an attacker would get access to the bootloading process and where are they. And there's really two levels. There's either the unlimited physical access. However, if an attacker has unlimited access, really the machine in the hand, and has all the time he or she wants to look at everything, then there are so many other possibilities to do that my first focus would not really be on making the CAN communication more secure, because at that point there might be many other things involved. The thing that I'm more worried about is the remote access. Maybe you connect for diagnostics, some diagnostic services that are shared somewhere into the cloud, or of course in the IoT world have maybe remote access, and on the bottom line it comes down that suddenly there's some sniffer or logger access available remotely, And that is the path that I definitely would like to protect. Not necessarily the unlimited physical access. However, this path, we want to make sure that the system is safe and cannot easily be compromised. So it's time to introduce our secure bootloader, and here it's even a secondary bootloader, meaning it's not part of the original chip. So there are several internal bootloaders. We'll review that later, and we will just simply add our own and try to make that as secure as possible. Let's start with some basics. At this point, allow me a small plug for our latest book, Implementing Scalable CAN Security with CANcrypt, because the methods introduced by this book is what are partially used also for securing this bootloader. And it's not really focusing on very specific methods. It's more of a framework supporting various security methods. One of the core functionalities that we'll also use in the bootloader is the secret exchange of keys in a complete different manner. So it's really a very CAN-specific encryption here. We'll talk about that. Then we'll have a pairing mode with encrypted and authenticated communication. The idea here is that only an authorized communication partner should be able to hook up with the bootloader and issue commands like delete the flash or even activate receival of a new code file. Let's look at the key exchange. So at some point, devices in any secure communication need to exchange some keys, and this method is based on something that Bosch already introduced quite a while in one of the earlier international CAN conferences, and they did it in hardware. However, that would require that you get yet another CAN controller where this is implemented in hardware. So we took the basic methodology behind it, do it in pure software and in pure messages, and so no hardware requirement changes in hardware. The basic concept is that if you look at a CAN message and you only have access at the trace, you see which messages are exchanged, you don't know where it originates from. If you have 10 nodes on the network and all of them can produce the CAN message ID 1 and someone sends it, well, if you look at the bus, you don't know who sent it. However, if there's 2 nodes involved in a communication and they agree to only use CAN ID, let's say 1 and 2, and they transmit something randomly with either CAN ID 1 or 2, then to the observer, you don't know who sent what. However, these 2, they know what they sent and know what the communication partner sent. And from that information, they can derive a single bit. So really, to cut this a little short, yes, it takes a while. It's slow because you can only derive 1 bit in one such cycle involving a minimum of 3 messages. You need a trigger message, and then randomly those 2 devices send a message and get a bit from it. However, it's fast enough to exchange a 256-bit key in about 4 to 6 seconds, depending on some of the timeouts used. So this can be used to exchange keys without the need to use high-end sophisticated encryption methods to protect the key. Another feature is the pairing that CANcrypt supports, and in the pairing is based on a symmetric key. It's initiated by the configurator or the device that will install new software to a bootloader, and it uses also the CANcrypt bit generation cycles to produce a random value that is added onto the symmetric key, so that you do not immediately see variations of these keys out there. So I'm not going into too many of the details here. it's quite a few steps involved. However, it's good enough to, as I said, exchange keys and to protect crucial commands like the bootloader activation or flash delete. When we talk about keys, we also have to talk a little bit about key management. The CANcrypt system supports a key hierarchy, so we have multiple keys available. For our bootloader, we have chosen to use 2 keys, a manufacturer key, which has a higher level, security level, than the system integrator key. The system integrator key could be given to a technician who is doing the software update, but this way the person doing the software update, the technician, doesn't need to have the manufacturer key to perform the update. Optionally, these can be combined with the local serial number, so if required and you really need to track individual devices, this allows you to kind of have an individual manufacturer or system integrator key for each serial number. We also have to talk about key identification. When you use symmetric key, there's not really a public part, so we had to introduce one for being able to find out which key is where. Imagine that you install 10 different keys on 10 different systems, and now one of these systems comes back and you don't know, oh shoot, which key did I have on here? Well, what we do here in this bootloader is we also associate with each key a 32-bit key ID, which is publicly readable. It's installed along with the key. So when the key is installed for the first time, also this key ID gets installed. And later when connecting to the device, again, even before making a secure connection, you can read out the ID. And so in a service case, you get a device, you don't know which key is in there, you read the key ID and then look in your internal key database if you have the matching key for this. So the security levels supported with our bootloaders can be summarized as follows. We have a global and a local protection, the global being the manufacturer key protecting the code, and the local key being on the system integrator level or service technician level protecting the connection. And the path for a firmware update would now be that at the manufacturer side you generate new code that gets both encrypted and authenticated using the code protection key. Then you can send this file on to your service technicians or maybe even the user if they are allowed to activate the bootloader, and that party has the connection key to authorize the connection. And then for the LPC 546 family flash memory, it would allow to do a connection using the connection key, transfer through this tunnel, so to speak, the code, and only the device here has again the code protection key to unpack the code and install it. Now with all keys, one of the biggest questions is, well, when and where are they installed originally? At some point they need to get into the system. Well, these must happen in a trustworthy environment. And this is really not too different from public-private key systems. In public-private key system, yes, you can throw openly around the public key. However, the private key, that you also have to be very careful of on where you use it, where you keep it, and that needs to be very protective and also only used installed in trustworthy environment. And so really that's where a root of trust begins. If you look at the term root of trust, you see this also with other chip manufacturers. I've actually seen somewhere recently that now you can get services where these keys or the private keys get installed directly at the chip manufacturer during the production process. And they claim, well, then you don't have to worry it and you trust us. Well, my biggest problem with something like that is it means that at this location where all these millions of chips are produced, there is somewhere a very large database with all the keys installed, and that must be a nice lucrative target for some of the hackers and hackers group out there. So I'm always prefer the best security you can get is stay under the radar, right? So as soon as you do something a million times, you get problems. But if here actually the benefit is if your production runs are smaller or number of keys are smaller, you don't need to worry too much about that. Nevertheless, where's the best point to install these keys? And typically the recommended place would be somewhere in between production, end of production, and delivery. If you use a third party for production and you don't want that third party to have the keys, then you have to find some way to program the keys in-house after production is delivered to you before you deliver to your customer. We made sure that for our bootloader, this is fully integrated also in the FlashMagic utility. So typically at the same time where you install the bootloader itself, that is also the place where you could have the default initial keys programmed. Let's talk about activating the bootloader. How do we activate it? Well, the typical process is that while your application runs, you need some method within your application to allow bootloader activation. So that really is highly application dependent. Maybe it's a service command, debug command or something like that. Nevertheless, what happens is once the application wants to enable the bootloader, it writes a boot code into a RAM location and does a reset, typically a watchdog reset. Now, out of a system or watchdog reset, the first code executed is the bootloader because the application will always be at later points in the memory, and that will verify if the RAM cells say, do they have the secret code to activate the bootloader? If yes, we activate the bootloader. If not, it possibly means that we are coming out of power-up reset or simply application didn't want us to start. Then we'll double check if we have valid code in the first place. Is the application in our flash valid? If yes, we start it. If not, we also remain in the bootloader. On this lower level, we, by the way, only use a regular 32-bit CSC because at this point, the application is already unpacked and flashed into the device. So the complex decrypting and authentication is only happening the first time the software is installed. Once it is installed, just the 32-bit CSC checksum is used. Let's now have a closer look at activate bootloader. So what happens once the bootloader becomes active? Well, there's a state machine internally, and number one, we start with a security delay. This increases delays on failures. Failures meaning if the pairing failed, typically because somebody used the wrong key, then we want to have an increasing delay to not allow brute force attacks to try different keys over and over again. So delay here will be similar as with your phones, where typically if you type in an unlock code several times wrong, it will only allow you to do the next try after several minutes. And same here, I'm not sure what the latest version does. I think we wait up to 5 minutes or so, and not immediately on the first failure, it's an increasing value. So this is the security delay. If all previous connection attempts were okay, we'll just start and wait to pair with the host to receive new code. And then once we are paired, we go into the commands where we wait for commands from the host and execute them. And these are CANcrypt commands, meaning they are both authenticated and encrypted. So that we can be reasonably sure it's not just a replay attack or something like that. once we activate code transfer, then we are in a code transfer mode where the code gets received and unpacked depending on the manufacturer key. Once the code transfer is completed, we go back in here, and if there's a power failure now, so it's not yet completed, it's the application loaded here is not really 100% completed until at the end the host here writes another confirmation that everything is completed. This is to ensure that there's really, even if you try to remove the host here in between, then it will fail because it needs to close the loop. So at the end, really both keys have been used and confirmed before we can start an application. Now, what do we need to do to update and generate the update file? Well, somewhere out of your compiler system, you get a hex file, and we produce you with a little, provide you a little utility that does all the conversions. So the first step we do is we generate a binary version of it, because this is in ASCII, it's just too big, so that it gets a little smaller, and add the 32-bit CSC. Then, taking the manufacturer key, we do the encryption and signing as a hash. That adds a security header and a digital signature to the file. And then at the final step, we add a file header. This is really just only for the host software to easily recognize the file format. So if a host opens these files, it can quickly see, oh yeah, this is one of our code update files. What's in this security header? The information we have in the security header is the bootloader version number to ensure that the bootloader version matches to what we have in the file. If these don't match up, then programming might not work, so we need that version in here. We also support firmware version number, because once you start using security, you should typically not allow downgrades, because this is one of the possible attack vectors, is that an attacker would first try to downgrade your system because older firmware maybe already has known vulnerabilities. So we want to protect from that, and it's an option, but once it's enabled, you will only be able to install upgrades, not downgrades. Also, we include the serial number into the file of the destination chip. So if you really want to make sure that this file can only be used with one specific chip and not be easily copied to multiple other chips, the serial number could go in here. And then, of course, the header needs the details about the encryption methods and signature methods used. If this is AES, SHA, and so on, we'll have a few more details on the available options there later. Now let's review the path of the data coming into the bootloader. So the host communicating with the bootloader initiates the pairing, erases the flash, and then starts the code transfer. So the file is sent to the bootloader without the file header. This is thrown away. Only the security header, binary hex, and digital signature goes to the bootloader. The host sending it, and on the bootloader needs to extract it, and with the information from the security header starts decrypting and programming it. And the important thing is that the very last block of the flash is only programmed if the digital signature matches. So if there's any mistake here in the digital signature, then you will have in your microcontroller the code, but the last section missing. So the section with the last block, including the CSC, is missing, and it will not get started. Also, of course, you will bring back an error message, and there will be no final confirmation from the host. Said to really complete the cycle, the host, when it didn't get any error message, will write a final confirmation also into the device.
Oh, I had a question just before getting into the next part about if there's a problem with the firmware update. So some kind of bug in the new version. I guess the way is you release another version.
Yes, that's the only thing you can do then. So really, if you would want to enforce a downgrade, you generate a version of the old code where only the firmware version number is higher again. But then, of course, this is a workaround which we actually want to protect you from. But I understand that sometimes you have to get your systems working again. And it's an option. We can disable it, but keep it in mind, as I said, this is the first thing attackers will try to do if they have access to older firmware versions, see if they can downgrade the device before they launch other attacks. Well, and Brendan, it's your turn anyway here. Yeah. So
okay. All right, yeah, just a couple of slides for me to comment on about the LPC product family. We already covered some more background on LPC in the other webinar. For those of you who already saw that, I'm not going to go and repeat all that information, but the work that ESA have been doing has been around our 54600 series. They've got a history of working with us on various other platforms, but this is our current platform for CAN-FD. Within the family of the 546XX series, there's parts that are enabled with CAN-FD. This is the kit that Olaf and his team have been developing with. It takes the standard 54618 MCU running at 180 megahertz. That board is fitted with a whole range of different interfaces, so you can do bridging between CAN and a whole bunch of other standards as well. I won't run through all of them here, but you can see there's plenty of flexibility there. We use the expansion connectors to add on a CAN-FD transceiver, and that's another NXP device, a TJA 1059. And this is all built on top of our MCU Expresso tool suite. So all the software that the ESA guys have been working with is all compatible with MCU Expresso SDK, and they develop with Kyle tools and MCU Expresso IDE primarily, but the software also works with IAR. Now we just announced a new part this month, the 54628, and this is a kind of superset part. And this runs up to 220 megahertz, has the same CAN-FD block inside. And for that, we have a board available that also has the LCD, and we will be making the CAN Shield board available that's in the CAN-FD kit pictured here. And that will become available in July. There's a block diagram of the 546XX series devices. Now, there's a lot of connectivity here that applies to all of the devices in the various packages, but not all of them are available on all part variations. As I said, to get CAN-FD, you need either a 5461X part or the 54628 device. But we do have other smaller footprint devices as well, small package devices down to 100-pin devices. So for more cost and space-constrained solutions, that's an option as well. And as I said, the 546XX series is very well suited for a whole range of applications because it's very flexible and offers a wide range of connectivity. So this is what we see as a great follow-on to some of our earlier CAN devices like the LPC 1700 family and 4300 family, 1800 family. And of course comes also with the same longevity programs, all the great quality and the worldwide support that you get from working with NXP on the LPC product line.
Well, thank you. I would like to continue here on the internal bootloaders available on the chip, because if we talk bootloaders, of course, we have to review what's available internally. And the guys at NXP really have enabled almost everything available here. As you can see, the in-system programming internal bootloaders work with UART, I2C, SPI, both USB ports, and of course the regular debug port is available. And if you used on-chip bootloaders before with UART, then the others work similar here, is that to activate them, you pull a certain pin low, and that activates, well, not just during a reset, or after a reset. So if the device comes out of reset, sees that one of these pins is low, the bootloader is activated and it remains in this bootloader. Now, This means as long as this mechanism is in place, you always have a backdoor. This comes back to what I said earlier. Do we have unlimited physical hardware access? Then this backdoor is available. Or do we only protect from remote accesses? Then remotely, these are of course not available. You can only communicate through CAN. Now, the interesting feature that NXP has provided is they can all be disabled. Now think about that for a minute. No, I won't give you a minute. Is if everything is disabled, then you are closing down completely this backdoor and entirely rely on whatever software you have installed in the device. So if you use our secondary secure bootloader and switch everything off, hey, yes, it works fine as long as you have the keys. If you lose the keys, sorry, no more updates. And Brandon really asked me for support reasons to keep this feature disabled. So our secondary bootloader per default has all of these enabled. You always have the backdoor to go through the programming through the debug port or the on-chip bootloaders. You have the option in our bootloader to disable it, but that's a code modification you have to do, and we'll of course tell you how it works, and you can of course read it in the data sheet, but I would be very careful with this because it really locks you out if the other secondary bootloader doesn't work anymore because you lost the keys, or there's something wrong with the CAN interface. Maybe the CAN controller got broken or so, then hey, yep, you're no chance to get in there. Let's review the software components required for the entire chain. So it's all available for free download. Well, not yet. We still do some final test. Our promise is that by Monday, the 10th of July, we want to have everything ready latest. But it will be on the NXP web pages, will be the download of the hex file, doing the bootloader. Then, of course, you need the FlashMagic tool. And depending on how many keys you start using, you might need to check into some key management. And for a very first go, some of the password generators and password safe softwares that you use to collect multiple logins on your PC, they can also be used here. So KeyPass is one that I use, that I like, and it could also be used to keep a little database of the keys generated here. Now, one would use the FlashMagic utility to do the initial programming of the bootloader and also the default keys. So both code protection key and the CANcrypt connection key would be programmed by default from FlashMagic here in a safe environment. And for the code updates, you need the secure packer utility that we provide that takes the hex code that you generate for an update and encrypts and authenticates it. And in future we'll have a separate also CANcrypt configurator utility. For now, a minimal version of that will be within FlashMagic, so you can also use FlashMagic to update your code through CANFD. Now, what we'll provide for free is the hex version in one configuration. Of course, we need to live from something too, so we'll also offer a commercial license which gives you full C source code access. And let's just briefly check on some of the differences. So the default is that I said we keep all backdoors open. If you want to disable them with the source code, you can do that. The bit rate on CANFD is fixed to 500 nominal and 2002 megabits per second on the data bit rate. And of course, with the source code, you can do any combination. And when communicating with the devices, we need to assign them a device or node ID that is also locked in the download version, in the free version. In the source code version, you can do any. In regards to the security method chosen, we have chosen as a default implementation AES-GCM. For those of you not too familiar with all the different algorithms, the nice thing about this one is that the calculation efforts around it are reasonable. It's using a 128-bit key, and in comparison to plain AES, which does only do encryption, GCM also provides authentication. So we have both encryption and authentication all in one go, whereas in with other methods you typically have to really use two methods, one for the digital signature used for authentication and one for the encryption. In the source code we kept all the security modules completely separate, and we're not using any own implementation here. We simply see what's available. Some on the ARM web pages embed also have several algorithms implemented, but once you have the C source code you could easily replace this with any combination of EAS, SHA-256 we have already tried. We haven't tried our asymmetric versions yet because we think for our average customer this will be kind of an overkill, but the options are there. Now, where are the security limits? Let's already do a first review. Well, we store the keys in regular flash. So if the in-system programming interfaces or debug interfaces are not closed down, they can be read out. Unless flash protection is enabled, the LPC 546 offers flash protection from read protection, so that needs to be enabled if you want to make sure that even locally they cannot be read out. Of course, an application installed will always be able to read it, but well, only the manufacturer can load the new application, so that should be not a problem. What we said before about key generation must happen in a trustworthy environment, and you really shouldn't use 1, 2, 3, 4 or birth dates or maiden names, you know all this stuff, right? So preferably they are truly random. And the weakest spot will probably be somewhere you need to store your keys. So where do you do that? If you use a password manager like KeePass, then you get access to all passwords in this database by one single login to this manager. And if you choose a 4-digit PIN here as the password to get access to all the other keys, I think then we don't need to continue negotiating if you should be using 128, 256 or even bigger keys. So I always say, as a rule over thumb, the keys should be protected as good as what they protect. Here they protect source code, so really you could also keep them just along with your source code, because wherever and how good that is secured, that's the same level of security right you need for the keys. One nice thing we can announce is that you don't only you don't need to take our word for how secure this is. NXP and Embedded Systems Academy decided together that once this is completed, we really should have a third-party review of the entire process. And we have contracted Math Embedded in the UK to do this. They have done a lot of similar work already, embedded work. They have been already a great help in the early stages for pre-selecting some of the algorithms we have chosen. So this is still work in progress. Obviously, they can't really start their work until we have the final software version. They will get access to all the sources involved and do a review on that, and they will not go all the way to do long-term penetration tests. It's more like, let's say, a security code review here at this stage. Now, with this, we are coming towards the end. Hey, good timing. And as I said, our goal is to have the files available starting Monday, the 10th of July. At the NXP web pages download into the demo tab. So it's will be at the same location where already the software of part 1 is located. And with that, I'm coming to the end and would like to only mention that you can also follow us on Twitter with our name there is CareEncrypt, or I would also like to invite you to follow our blog at esacademy.com blog. So, Brandon, you are looking at all the questions. I didn't. Is there anything else we need to answer?
Well, we had a few come along the way. Unfortunately, I had a bit of an issue halfway through, so I couldn't ask some of them at the right point. But we are a little short of time. But briefly, the question came in about applying these kind of methods to over-the-air updates. There's really nothing here that wouldn't apply as well to an over-the-air update versus a wired update, right? It's just a question of how the infrastructure of the system's designed, correct?
Correct. Of course, we have to know that on the lowest end, we'll always have CAN-CAN-FD communication, but how the code file gets to this host that connects there, it could be also a complete remote process. The problem with completely remote processes is always that if you don't have a service technician involved, then there is some machinery that is on the net that has some of the keys, so we would need to do a closer review there. So what we did here is more the intention of having still a security person involved, but how that a technician involved in updating the code, but how the code gets there, that can be any way.
Right. Okay. Thanks for clarifying that. So the other question was related to the use of OTP for key storage, but I think one thing that's important for people to understand is that you know, Embedded Systems Academy offer services to do bespoke bootloaders or work with the customers as part of your business model, correct? So if people want to adapt and change the bootloader, they can do that working with you.
Yep. The reason we didn't put it in the OTP is that the security level in CANcrypt allows reprogramming keys at the same security level. So if at some point you want to change a system integrator key because maybe well, you fired someone, or this a person is not trustworthy anymore, then these keys can be modified, but of course you need to do it before that person has access. So we can put them anywhere. They could be also in OTP, but we didn't. We wanted to be more flexible on it.
Yeah, and that was really the point I was making with your the free example bootloader. We're trying to do something flexible, but if somebody wanted to manage that risk of not being able to modify the key, they can do that by working with you as an adaptation of the bootloader, correct?
Correct.
Yeah. Okay, well, we are out of time now. I think we covered all the questions open there. Olaf, thank you very much once again for helping us with these webinars. And thanks again for opening up your contact points here for the people listening. People can also post on community.nxp.com. And we do work with ESA to have them help with some of those questions that maybe are a little require a little more expertise from them. So it's a great way to share your thoughts and questions with the community. Thanks everyone for dialing in. We will post the recording of this session. The slides are already there in the handout section if you can quickly grab them before we end the webinar now. But they'll also be posted on the site where you registered. So thanks everyone. Have a great summer. We will be doing some more webinars later in the year as the summer vacation season comes to an end. So we hope we'll see you there again soon. Thanks very much.
Thank you, Brendan. Goodbye.
Thanks, Ola.